Hi and hello everyone. So last time we left off with our orthographic projection where we learned how to map from one space to the other. And now we're going to learn all about perspective matrix. So what's the perspective matrix? Well, it's a matrix that essentially has a depth to it. So last time we just went through orthographic camera, which admittedly, we looked at it from the side of just mapping from one space to another, right? We had this idea of -1 to one space, and then we mapped it to maybe -20 to 20 space, right? We learned how to map that space. So that's kind of going to be important for this video as well, and especially when it comes to z axis. So we will be working a lot with z. But the perspective, it has this depth perception. What does that mean actually? Well, if you look at this image here, you know that these tracks are same everywhere. So you know the distance between this track and this track is same everywhere, right? But we have this kind of perspective, right? As we go further away, everything appears smaller. So we're going to play with it. And what does that mean? Well, that means that we're going to set up our camera in such way that if z is further away, x and y get scaled down, and therefore we get this kind of depth perception. Okay, so let's start with it. And first step, I just want to showcase rotation, and we're going to add a new matrix here. So I'm just going to zoom it up a bit. Appearance, I think it's somewhere over here. It should be zoom in. Alright, I think that's big enough. So we're going to have rotation X, and I already got suggestion here, and it's a good suggestion based on what I see. So basically, if you want to rotate around X-axis, you just leave X term, or whatever you want to call it, the first row is identity row, and then you offset this, right? And then you have cosine minus sine and sine cosine. Same as here, but here it's actually rotating around z. Here we're rotating around x. So you can actually just maybe write that as well. But the other thing that I wanted to have is just that we're going to need to multiply matrices. And so I would suggest maybe going to GitHub, which is in the description of the video. And then you're going to see, I'm just going to paste it over here, you're going to see a multiply basic operation, and you know how to multiply matrices, right? So this is just, I don't want to write this in this video, right? But it works, it just multiplies two matrices and then gets the result here. With that said, just so that you're aware, this math is made for simplicity and just for learning purposes. So I would usually not create a new matrix every time. Rather, I would have maybe third parameter, or maybe as a first out, and that's the matrix that I would assign the values to. So it will be similar to GL matrix, but this is just for learning purposes. Therefore, I always create a new matrix, and here we can see the values. So it's just for simplicity. It's not the most optimized way, but it's clear what's happening. Then, if you have that and the rotation around the x-axis, maybe we can showcase that rotation. So we're going to go to our main, and here, what did we have here? We had this translation, but now I'm going to say matrix multiply. So we can just move translation a bit, and then we can do this rotation around the x-axis. And we already had this angle, right, around the x-axis, my bad. So if I was to refresh it, you can see already that it rotates. It just happens to be our distance is at 1, so as it rotates, the coordinates go above the z value, right? At some point z is above 1, and therefore only half of the triangles is seen. We can either adjust translation or this part, which is depth, but here I'm just going to go with minus 1, and then I'm going to actually adjust translation. So yeah, so just as it rotates, we're going around. But as you can see, it's actually rotation around the x-axis. So as it rotates, there should be some depth to it, but there is none. And so we're going to focus now on that. So let's see how can we solve for that. If we imagine, and here, okay, here, let's say that we have some axis, which is the axis, and here we might have some point P, right? And here is our projection plane, and let's say that here it's 0, here it's 1 and Z. And the whole idea of the previous video with orthographic projection was just to use this P, right? Which is at some Z, arbitrary Z, which might be 10, might be 20, it doesn't matter, but we kind of projected it here. And orthographic is called parallel projection because it just projects parallel. I mean, it's not super parallel here in my drawing, but you get the idea. So we just projected it here, but the point P can be here, and then we projected it right here as well, or it can be here, we projected it here, but the point is it's parallel, right? So the X, if we imagine that this axis is Y actually, the Y is always the same, even if we project this to this projection plane. Y here will be the same as Y here will be the same as Y here. So that's why it's called parallel as well. But here, let's imagine this case. Let's say here is Z, here we have 0, 1, and here we have some P. And here I just projected to 1 to far value of our depth buffer, but it can be somewhere over here as well, right? That's the point of that buffer. So usually it goes from 0 to 1 depth buffer or Z buffer. And usually, right, if you want to draw to it, you draw to these values, and you can set it up so that values closer to 0 appear as closer. But all right, let's discuss this case. But let's imagine this case, right? Our P gets projected here. So what did change, right? Well, first of all, P did change, but also if you imagine that this is Y, and the P can be point X, Y, Z, right? But I'm just for simplicity saying that this is Y axis, right? This is Y axis, and this is some point Y. And as you can see, we scaled Y, let's say with value Z. It's not going to be Z, it's going to be some far minus near. So it doesn't have to be Z, but let's just say that we scale it over Z and we projected it to this one. As you can see, Y is scaled down, Y is lower now. So it's same if it's here, right? It gets projected, Y is less than a Y here. So that's kind of how it works. And you're going to figure it out if you haven't already. But for start, what we're going to do is we're just going to divide our Y by Z, right? And X similarly. So we're going to divide all the values by Z. And Z divided by Z is 1. Therefore, it's going to be written to this one value. So if we imagine, I already mentioned, we have a 0 to 1 buffer. For now, we're just going to project to this one, so the far end of the buffer. So as I mentioned, if Z value, if our depth value is greater than 1, then it's not going to be drawn. And same is if it's lower than 0, then it's not in clip space, and therefore we're not going to see it. So how can we project to this? All right, as you remember, and maybe I should just do this slower, we had this idea of our camera. So we had, well, X is not important here, right? The Y is not important here as well. And here we just had X, Y, right? Z, and sorry, this is not double, it was 1 usually in our shader, right? If you remember. So if I was to go, maybe I can do that somehow. Well, let's just check it here. If I go to shader, we always had this position, right? And position is X, Y, Z, and then we had 1. So this one is important for now. So let's go further. I'm going to explain why 1 is important. But we can imagine that our Z camera, we had something like this, right? And then 0, 0, 0, 1. And when we multiply it, we get X, Y, Z. and 1. And this one was important, right? I mentioned that somewhere in the pipeline, after the vertex stage, everything or any number that's here, right? It doesn't have to be 1. Let's just call it component v. So at one point, our x is going to be divided by it, our y is going to be divided by it, and our z is going to be divided by it, right? But if we place z here, right, somehow, and I'm not going to do it shader, we're going to use matrix here. That's why I drew it. So it's not going to be like this. It's going to be x over z, right? Because it's z at the end. Z and z over z, right? And I already mentioned this is going to be equal to 1. So we're going to just project this 0 to 1. We're going to project to this one. So how can we do that with a matrix? Well, if we place 0 here and place 1 here, what has happened with the last term, right? This term v. So maybe I should just redraw this again. So we had x, y, z, and then we had 1 as usual. And our matrix, right? Not important, and z is not important either right now. So we're going to deal with it. But if we placed it here, right, what are we going to get for this last row? So x gets multiplied by this term here, so it's 0. Y gets multiplied here is 0 plus 0. Z gets multiplied by 1, so therefore we get z, right? And 1 gets multiplied by 0, it's still 1. So this last term is going to be z, and that's important. So let's just try to do that matrix, and you're already going to see a result. So you're probably going to get idea of how it works. So we're here, and I'm just going to do, what am I going to do? Well, I'm just going to say public static. It's going to be perspective, and no parameters for now. So you're going to see that it works even without complicated parameters that you're usually going to see. And here I just mentioned that here we're going to have 0, and here we're going to have 1. And I'm going to go to my main, and here somewhere, if I could find it, where we were setting the camera, here. So we can just leave orthographic for testing purposes, but I'm going to say perspective here. And then maybe I can exit full screen. Somehow try to get rid of this mess. And here you can already see that it works, and it works beautifully, right? It rotates, and you can see already depth perception. I'm just going to move it a bit back, and this is going to be fine. We're going to see it even if it's at 1, right here. So as I mentioned, we're actually drawing at 1, but our z rotates, but we're still able to see it. Why? Well, because, like I mentioned, we projected everything to 1. If I go to drawing here, right? So everything is projected to exactly 1, right? It's just that our x and y's are scaled. So this kind of works, and it works perfectly. So I need to get back. But the problem is, right? So let's get rid of this. The problem right now is it's our z is always at 1. So if I was just to increase z in shader by some small value, we would not see anything, and I might do that actually. So let's go to a shader just to confirm. So I'm going to say out position that z plus equals 0.00001. And we actually see it. It's amazing. Okay, we don't see. So I guess the precision here is the problem, right? If we go further away, it may be something with precision, but we don't see it. But if I was to subtract it by it, we should see it, right? Because it's still in 0 to 1 space. But if I do plus, it's not. Okay, that's clear now. Okay, so how can we solve for that? Okay, let's see how can we map that. So our idea is right now our z is always equal to 1, just because we divide everything by z always, so z gets mapped to 1. But we want to actually move it to some 0 to 1 space, and we want to have arbitrary space, right? So that we don't have to have necessarily 0 to 1. So our idea is, okay, we can have 0 to 100, but let's just map it to 0 to 1 space. So how can we do that? Well, if we know that we had x, y, z, and this one, and then we had some matrix. So let's ignore x for now. Let's ignore y for now. But z, as you remember from the last part, it had scaling part and then it had translate part. And here we already determined that this last column is going to be, third row is going to be 1. And as you know, our scaling part, what was it doing? Well, we had 0 to 1. We could scale that, for example, to 0 to 5 space. But our translate part was responsible for maybe mapping this to, let's say, minus 2.5 space to 2.5 space. So we could remap that space as well. So how will that look like? So if we know when we do multiplication here, sorry about this, let's just ignore x and y and let's look at z. So we had, we're solving for z part, right? So we had x times 0 is 0, plus y times 0 is 0, right? Then we had z times s, so we had zs, right? And plus 1 times t, right? Plus t. So we know that we have zs, right? Zeros, or better yet, z scale plus translate part. And here last part, right? We had x times 0 is 0, y times 0 is 0, z times 1 is z, and then 1 times 0 is 0. So this last part was actually z, right? Once we solve it, we should have something like x, y, and then we had this scale, z plus translate, and then the last term was z. Oh my god. Okay, it was z. And then everything gets divided by z, right? This over z, and then this over z, and then this over z. So let's go with this one. So we have this s over z, z. So we can solve for this, right? That becomes simple. And then we have s plus t over z. And we have to solve it. So how can we solve that? Well, if we know that, for example, we're working near z, so we have some z near. When z is near, what's the result? Well, it's 0, right? But we also know that plus st over z far, and when z is furthest away, it's 1, right? Because we always map to 0 to 1 space. So we can leverage that. Let's solve for s here. So we just have s is equal to, and when we move this to the right side, it just becomes negative, minus t over z near. So we can plug that s here. So we're going to have minus t over z near and plus t over z far is equal to 1. Okay, we can solve here. Where is my mouse? So we have z near and we can say z far, right? So we can multiply here these terms, and then we have z near times t, right? So okay, I'm going to write this one first, just because I prefer to have negative on the right side. So we're going to have t z near minus t z far, right? And is equal to 1. So we can just multiply by this, so it gets rid of this, and then here we have z near z far. And we can also rewrite this. We can just move t here, so we have z near minus z far is equal to z near times z far. And at the end we can just divide by this, right? So we're going to have t is equal, because we get rid of this, and then divide here. So z near minus z far, right? And so we solve for t part. Oh, sorry, this multiplication. This is z near minus z far. So we can actually add those parameters to our matrix. So let's just add to our matrix near of type number. And I'm going to, by default, have 0.01. I do recommend that you use maybe some value close to 0, because it might get messy if you use 0. It's because of divisions and everything. Alright, so we're going to have this. So we have our perspective, near and far. So we had this translate part, which belongs here. But I'm just going to use this. And then we're just going to say, okay, so that goes here. And what did we have? Well, if you take a look how we solved for it. So we had near times far, near minus far. So let's just write it. So we had near times far over near minus far. Okay, we solved for that part. And you can see that it still works, right? I refreshed it, it still works. So that's good. If I break it here by doing times 2 or 50, okay, it still kind of works correctly. Let's try to break it somehow. Okay, yeah, you can see it works. All right, let's go for this scale part. And scale part is now like super easy. So for the scale part, we just have to take, what was it? This first thing here, which we had, and this was near, this is equal to 0, right? We can take that. So let's rewrite it somewhere and try to solve it. Let's see where I do have empty space. Maybe somewhere here. Okay. So what did I mention? So I mentioned that if our s plus t over z near is 0. So we solved for this t. So we're just going to say s plus, and it was z near times z far, right, over z near minus z far. Then we can do this. We can just write z near over 1, right? And that checks out. So what are we going to have? Let's try to solve for it. So I'm just going to write it like s, then minus, right? Because I'm going to move all of this to the right side, right? The equation. So minus. So here we have 1 times. So we're just going to rewrite that 1 times anything is 1 z far, and here we need to do some math. So we can just write this as z near, and then z near minus z far, right? This times this, and then we can get rid of z near, and we solve for our scaling part. So it's negative z far, right, over z near minus z far. Okay, let's try to write it. Negative z. So that's this part here. So we had negative far over, not far minus near, rather it was near minus far. And it still works. It still works. So let's just try some testing here. So we should be able to translate somewhere far, and it should be way smaller, right? Because our far z is now 100, right? Because, for example, if I was to change it, here's our perspective. Let's say 0.01 for near, but let's say that far is at 5, right? And our translate is now at 5, so it's quite far away. If I was to place it at 3, we would not see anything because it's quite far away. We see only half of it, right? Because as you can imagine, our far plane is 3, and here we translate it to 3. So as it rotates, some of our z's are actually about 3, so we don't see anything. But if I were just to place it to 2.5, we should see everything. If I was to place it at 1, it should appear closer because it is closer. All right, we solved for that part. That wasn't too hard. So next part is let's try to solve for x and y and how can we scale them. Well, you can already use stuff for the orthographic camera, but usually we have something called field of view, right? And you probably already know what field of view is. I'm not going to explain it. If you ever did any high-level game development, you probably know field of view. But anyway, let's say that we're watching somewhere from over here, and then we want to see maybe this point, but we're not going to see this, let's call it R point. We're not going to see it because, you know, if you imagine that this is our field of view, right? And in a negative direction, this is also field of view. So we're going to see everything that's in our field of view, but if something is above, we're not going to see it, right? And the field of view can be expressed as our angle and then angle as well. So we had this dividing, right? Because we have positive space, right, 1, but we also have negative space, -1, and that's true for both x and y. So we could be looking either x or y, but usually we can also say, nah, this is good. This is good. Let's say C. Okay, and how do we solve for this, right? For our field of view. If we imagine that we're player here, or yet somewhere over here maybe, and then we're seeing all of this, So what will our field of view be? Well, as you know, field of view, we can express this as right angle, and then we have something called opposite side, and then we have something called adjacent side, right? But what's the opposite and adjacent? Well, it's tangent, right? So tangent of angle is equal to opposite over adjacent, right? So we can just take tangent of angle, but since our field of view is this, right, all of this, and we have half an angle for our positive and half for negative, we're just going to divide it by 2. Sorry, not by z, by 2. So our solution is tangent of angle over 2. So we can write that, and it's going to be somewhere over. So let's go to our matrix. But as you know, we usually had to this division, right? 2 over from the last time, but now it's just going to be 1 over. 1 over angle. So we're going to have scale x is r0 c0. It's going to be 1 over, and here we're actually going to add field of view. And by default, let's say it's 90. But I forgot one thing. And that's it needs to be in radians. So let's quickly add some math-util class. And here I'm just going to have export class and return sorry, public static function. So we're going to have degrees, we're going to return degrees times math pi over 180, and that's going to give us our radians. Okay, sorry about that, postpone. But anyway, so we have this radians. I'm not going to explain because it's pretty simple. It's just x over degrees. You can solve for it. But let's go further. So we're going to just have here const radians, and it's going to be math-util 2 radians field of view, and then we just, what did I mention? We need tangent r over 2. And then the same for y. C0, 1C1. And we don't see anything. Because of course we changed our parameters. If I could find it. So we also need to add field of view here. Okay, and we can see it. So if I decrease field of view, everything is going to be zoomed in. If I increase it, it's zoomed out, because bigger field of view, the smaller objects appear, right? You can see more stuff. Okay, that solves it. And one last thing that I have to solve is actually, because usually you're going to see second parameter. If you ever used any math library, you're going to see aspect ratio, as a parameter, and you're going to see issue right now if I was to change our class. So let's say something like this. So you can see that it appears stretched, right? So we just need to figure out to correct it for the aspect. So we can do that here. So we can say canvas width over canvas height. So nothing is solved yet because we need to edit our matrix. And here we can say aspect ratio, and by default I'm just going to kill 1. And then we need to multiply here times aspect ratio, or here. Okay, let's just see. Okay, it's corrected for aspect ratio. It's just everything is big, so we can zoom that out a bit, or just translate it a bit further down. Okay, cool. Now it's correct, and it's corrected for aspect ratio as well. And the last part that I actually wanted to just quickly comment, because I wanted to solve it, and you're going to probably have to copy paste this, because we're going to be dealing with this next time. I'm just going to copy paste it quickly. So we had, I'm going to have, because it would be nice to work already with 3D objects, but you're going to see what's happening if I add 3D object. So I just had here create cube geometry. So you can copy it now, or you can copy it in the next part of the video, because this is just in the next video, because this is just for this showcase. We're going to be solving for it next time. So if I say here create cube geometry, right, we have our cube, but we don't do any depth testing, right? As things are written out, they might be written in lower z or over higher z, or if we had higher z, some might be lower. But anyway, to solve this and actually to have it show correctly, we need to do depth testing. So that's what we're going to do next time, so that we can have proper 3D objects that work correctly, right? So now we have this z fighting. I'm not sure what's happening, but for the next time, so we're going to be dealing with this depth testing. So hopefully you enjoyed this video. If you liked it, maybe like, subscribe, and until next time.